In this video, I'm going to show you how we can find integrating factor for non-exact differential equations. Sometimes differential equations in the form of m of x and y dx plus n of x and y dy equal 0 are not exact differential equations. Remember that a differential equation in this form is an exact differential equation if the partial derivative of m, the expression here, the function that we have here, the coefficient of dx, if the partial derivative of m with respect to y equals to the partial derivative of n with respect to x, then the differential equation is an exact differential equation. But sometimes these two are not equal to each other, and so the differential equation is a non-exact differential equation. But fortunately, if we multiply the differential equation by a function, we can convert the differential equation to an exact differential equation. The problem is that finding that function, finding the factor of integral, we name that function the factor of integral. Finding that factor of integral usually is not easy. Here we want to learn how we can find the integrating factor. Two special cases of integrating factor are more important, and in this video we want to talk about those two types. The first type is when the integrating factor is a function of x. But how we can find the integrating factor is a function of x? First, for finding the integrating factor, you have to find the partial derivative of m with respect to y minus the partial derivative of n with respect to x. Note that this difference is a non-zero expression, because if these two be equal to each other, then the differential equation is an exact differential equation. So this difference is a non-zero function. If we divide this by n, note that n here is coefficient, the function that is multiplied by dy. So if we divide this by n and we get a function of x, so if we suppose that this expression is a function of x, then the integrating factor, the function that if we multiply the differential by that, the differential equation is an exact differential equation. The integrating factor can be evaluated from this expression. The integrating factor is e to the power of integral of this expression, so m sub y minus n sub x over n dx. By calculating this expression, this integral, we can find the integrating factor. But it is possible that when we divide this by n, we cannot get a function of x. So in that case, maybe this helps. If we divide the same thing by negative m, note that here we divide this by n, but for y, if we divide by negative m, and note that negative m is coefficient of dx, it's the function that is multiplied by dx. If we divide this difference, the same expression that here we had, by not m, negative m, and we get, if we can get a function of y, then the integrating factor is e to the power of integral of m sub y minus n sub x over negative m dy. These are the two more important integrating factors for non-exact differential equations. From this formula, we can find integrating factor in terms of x, and from this formula, we can find integrating factor in terms of y. We have to check to see which one of these works for a differential equation. Now let's do our first example. Our first differential equation is y to the power of 3 plus 4x dx plus xy squared dy equal 0. First, note that this given differential equation is a non-exact differential equation. This expression here is m and this expression is n. If we take derivative of m with respect to y, derivative of derivative of this expression with respect to y is 3y squared. And derivative of n with respect to x is y squared. And as you can see, these two are not equal to each other. And so the differential equation is a non-exact differential equation. So let's first calculate this difference, m sub y minus n sub x. As we see here, m sub y is 3y squared and n sub x is y squared. The difference is 2y squared. Now we have to check to see if we divide this expression by m, actually by negative m, not m, or n, which one is helpful for this differential equation. If we divide 2y squared by n, y squared and y squared here cancel each other, and then we get a function in terms of only x. But if we divide this difference by negative m, this expression cannot be simplified with this expression. So for this example, this integrating factor works. Again, note that if we divide m sub y minus n sub x by n, as here we have, this expression m sub y minus n sub x is 2y squared. And if we divide that by n, which is xy squared, y squared and y squared cancel each other and 2 over x remains. And note that this expression is a function of x, and it shows that our factor of integral can be calculated from this formula. So our integrating factor mu of x is e to the power of integral of this expression 2 over x dx. Integral of 2 over x is 2 ln of x. Note that integral of 1 over x dx is ln of x, so integral of 2 over x is 2 ln of x. But before we multiply our differential equation by this expression, let's first simplify our integrating factor. We can bring the coefficient 2 to the power of x, and we can write this as e to the power of ln of x2. But we know that, in general, e to the power of ln of any expression equals the same expression. So e to the power of ln of x2 equals x squared. So this equals x2 finally. So x squared is the integrating factor for this differential equation, which means that if we multiply this given differential equation by x2, we have an exact differential equation. So let's multiply our differential equation by x2. If we multiply this expression and this expression by x2, we have x squared y to the 3 plus 4x to the 3. Note that we multiply each term by x2 plus, if we multiply this by x2, we have x to the 3 y squared dy equals 0. Now we expect that this differential equation to be an exact differential equation. Before we solve this differential equation, let's check to see if really this differential equation now is an exact differential equation. Note that now this expression is m and this expression is n. M sub y, the partial derivative of this with respect to y is, if we take the derivative of this with respect to y, we have 3x squared y squared. And n sub x, the derivative of this with respect to x, is exactly the same, 3x squared y squared. And as you can see now, these two are equal to each other. And so this shows that the differential equation is exact differential equation. So we have a differential equation which is exact differential equation. Now we can solve this exact differential equation. If we remember, for solving exact differential equations, first we have to integrate m with respect to x. So first we have to calculate integral of m dx. So we have to calculate integral of x2 y3 plus 4x to the 3 dy. So dx. Integral of x2 y to the 3 with respect to x is x to the 3 y to the 3 over 3, which we can write it as 1/3 x3 y3. Note that when we want to integrate this with respect to x, y to the 3 is a constant, so we just copy y to the 3 and only we integrate x2, and integral of x to the 2 is x to the 3 over 3. And integral of 4x to the 3 with respect to x is 4x 4 over 4, which we cancel 4 with 4. Integral of 4x to the 3 is x to the 4. Don't forget to add a function in terms of y as the constant of this integral. Because we are integrating in terms of x, the constant can be a function of y. Because with respect to x, a function in terms of y is a constant. Now, if you remember, for finding this gy here, we have to differentiate this with respect to y, and the derivative of this with respect to y must be equal to the function here, to the n. So, if we differentiate this with respect to y, the derivative of this expression with respect to y, derivative of this term with respect to y, derivative of y to the 3 is 3y2. If we simplify 3 with one term, derivative of this term with respect to y is x to the 3y squared. Derivative of this term with respect to y, because we don't have any y, is 0. And derivative of g of y with respect to y is g prime of y. And it should be equal to n, which is x3y2. From here, g prime of y is 0, which means that g of y is a constant. Note that for finding g of y here, we integrated 0. Integral of 0 is 0 plus c. Because we integrate 0, at least we have to put constant c here. So the function here, the constant function, is a constant function. And so the solution of this differential equation can be written in this form. 1/3 x to the 3 y to the 3 plus x4 plus c equal to another constant, which we can name it, let me name this c1, which we can name the other constant c2. If we move this constant to the other side, c2 minus c1, because these two are constant, the difference of two constants is also a constant. So we can write this answer in this shorter and better form. Plus x4 equals c. So from here to here, I moved this to the other side. The difference of these two constants, I named it c. And this is the solution of this exact differential equation. Let me show you one more example of a non-exact differential equation, which we can make it an exact differential equation by finding integrating factor. But actually, let me show you the shorter way, the shortcut method for solving this exact differential equation. If you remember from my video about exact differential equations, we have a shortcut method for solving exact differential equations, which is really helpful for finding this solution faster. Let me write down the differential equation again here. X to the 2, y to the 3 plus 4x to the 3 dx plus x3y2 dy equals 0. If you remember from that video, this is the shortcut method. For finding the solution of an exact differential equation, only we have to integrate whatever is here, m, integral of m dx, plus integral only the terms here that are independent from x. If you remember, this was the shortcut method. So we integrate whatever is here, but when we want to integrate n, we only integrate the terms without x, the terms that are independent from x, that are not a function of x. Here in n, we have only this term, x to the 3, y to the 2. And as you can see here, we have x. So n star, which I mean only the terms in n that are without x, that are not a function of x. In this example, we don't have anything for n star, so here we have nothing to put. It's actually 0. So only we have to integrate m with respect to x and set it equal c, and then you can find the answer easily. Integral of x2y3 plus 4x3 dx equal c. Again, because everything here is a function of x, so we don't have anything to integrate with respect to y. That's the reason we don't need to put this part here. Integral of x2y3 with respect to x is 1/3 x3y3. Integral of 4x to the 3 is x4 equals, and this is the solution of this exact differential equation. If you compare this answer with the answer we get here, you can see that these two answers are the same. Now let me show you another differential equation. The given differential equation is 6xy to the 3 minus 4y to the 3 plus y dx minus 2x plus 4y to the 3 dy equal 0. First, let's see, is the differential equation an exact differential equation or not? If I name this m and I name the other one n, m sub y and n sub x, the partial derivative of m with respect to y is 18xy squared. Derivative of y to the 3 is 3y squared. If we multiply 3 by 6, we have 18xy squared minus 12y squared plus 1. And the partial derivative of n with respect to x is only negative 2. Note that the derivative of 2x with respect to x is 2, but here we have a negative here. Don't forget this negative. So n here actually is not only this bracket, n is this bracket with that negative. So it's better to choose n as all of this. As you can see, it's obvious that these two are not equal to each other, and so the differential equation is a non-exact differential equation. For finding the integrating factor, it's always better to calculate this m sub y minus n sub x. This minus that. If we subtract this from that, we have 18xy squared minus 12y squared plus 1 minus 2, which we can write it as plus 3. Note that all of these terms are a factor of 2. So if we factor 3 from there, we have 6xy to the 2 minus 12y to the 2 plus 1. Now, if you compare this with here, you can see that if we divide this by m, or actually negative m, this part and the m cancel each other. So here it is obvious that our integrating factor is a function of y actually, because if we divide this by this, they can simplify each other. But dividing this by n is not helpful like the previous example. In the previous example, when we divided m sub y minus n sub x with n, we get an expression in terms of x. But here, dividing this by n is not helpful, because this cannot be simplified with n. So here, for finding the integrating factor, we decide to divide this by negative n. Don't forget this negative. I know it's hard to remember, but this is how we can solve differential equations. Usually it's a long process solving differential equations, and if you make a mistake in one of the steps, you cannot continue from that point. And if you continue, you cannot get the answer. Anyway, let's continue. So we divide this by negative m for finding the integrating factor. 3 bracket 6xy squared minus 12y squared plus 1 over negative bracket 6x y to the 3 minus 4y to the 3 plus y. If you pay attention to the y, all the terms are a factor of y. So if we factor y, we have 3 times 6xy squared minus 12y squared plus 1 over negative y times 6xy to the 2 minus 4y squared plus 1. As you can see, this bracket and this bracket cancel each other, so we have negative 3 over y. And as you can see, this is a function only in terms of y. So we can find the integrating factor for the differential equation from this formula. Integrating factor, which usually we show with mu, actually here we can say mu of y because it's a function of y, is equal to e to the power of integral of this expression. So integral of negative 3 over y dy. This integral is negative 3 ln of y. If we bring this to the power of y, we have e to the power of ln of y to the negative 3, which finally is y to the negative 3. So by multiplying the differential equation by this, we can convert the differential equation to an exact differential equation. If we multiply the differential equation by y to the negative 3, the differential equation can be written as 6x. Note that y to the negative 3 multiplies by y to the 3 and they cancel each other, and only 6x remains because y to the 3 times y to the negative 3 is actually, because this is reciprocal of that, is 1, and only 6x remains. If we multiply y to the negative 3 by negative 4y to the 3, we have only negative 4. And if we multiply y with y to the negative 3, only y to the negative 2 remains. So plus y to the negative 2 dx minus 2x times y to the negative 3 plus 4 dy equals 0. So if we multiply everything here by y to the negative 3, we can get to this expression. And this new differential equation must be an exact differential equation. You can easily check that the derivative of this part with respect to y is equal to the derivative of this part with respect to x. For solving this exact differential equation, here I prefer to use only the shortcut method. If you want, you can solve this exact differential equation with the usual method. But here, to make the video shorter, I prefer to only use the shortcut method for solving this exact differential equation. Based on the shortcut method, we have to integrate everything that is here, 6x minus 4 plus y to the negative 2 dx. But here we have to only integrate the terms that are independent of x without x. This term has x, so forget this. We don't need to integrate that. But this term, in this term, we don't have any x, so we have to integrate only this 4. But don't forget we have a negative here also. So plus integral of negative 4 dy equals c. By finding these integrals, simply we can find the answer. Integral of 6x dx is 3x squared. Integral of negative 4 is negative 4x. Integral of y to the negative 2 with respect to x, don't forget we are integrating with respect to x, so this term here can be considered as a constant when we integrate with respect to x, and integral of y to the negative 2 is y to the negative 2x, and integral of negative 4 is negative 4y equals c. So this is the solution of the differential equation. I hope by watching this video you have learned how to find integrating factor for non-exact differential equations. I know finding integrating factors is a bit tricky and it needs a lot of practice. In the next videos I try to show you more examples. If you like this video, please subscribe to my channel and see you in the next videos.